Hello everyone. I was reading through the forums today and I saw we were having some issues with finding radical expressions, or excuse me, simplifying radical expressions. So what I decided to do is I wanted to pop into the study plane here, work through a couple of examples, show you how I solve these using the factoring method, and hopefully that'll help you guys get these answers, especially as we get to some of the more difficult ones. So I'm in Chapter 8, Section 1, Question 19 of the study plan, so you can follow along there if you'd like, but I'll also work them out here. And we're given a problem that says find the root, and then we're given the cube root of 27. So they're asking us to find the cube root, and I'll go ahead and write it here so you guys can see what I'm doing, but we're asked to find the cube root of 27. Okay, so there's a couple different ways we can try and do this. The book is going to show you trying to find perfect cubes. So what they'll say is 27 is the same as 3 cubed. And if we take the cube root of a cube, these things are going to offset, and we're going to be left with just the radicand, the value 3. So what they're going to say is the cube root of 27 is 3, and we found that by knowing that the perfect cube equivalent of 27 is 3 cubed. Well, as we get further into the course, it's going to be harder to spot these perfect cubes. So what I'm going to suggest is that we learn how to factor these so that we can apply these to a wider range of problems. So let's go ahead and take this same problem, cube root 27, and actually all I'm going to focus on is the 27 right now. And we saw that 27, and I'm going to create my factor tree. So I can say 27 is the same as 3 times 9, and 9 is the same as 3 times 3. So all I've done is broken my problem into its prime factors. I go back and I circle my prime factors, and my prime factors are all right here. So again, we've now just shown where this 3 times 3 came from, so I can write it as 3 times 3. And what we're looking to do with cube roots is we're trying to find what the index is telling us. The index tells us I need 3 factors, right? I need 3 factors in order to pull something out to the outside, or what I'll call in front of the radicand. And as you'll notice, we have 1, 2, 3 factors of 3, so I cross them out, and I move them to the outside, so I'm left with just 3. My radicand is now gone. So I can actually get rid of that, and I'm left with 3. And the reason I write it this way is because now we can do a problem such as 54. So what I'm going to do is, right over here, I'm going to draw a little line separating these two concepts. I'm going to switch colors back to, we'll go back to the black here, and I'm going to ask you to find the cube root of 54. So what you may want to do is pause the video and try and do it on your own. I'm going to go ahead and keep working right here so you guys can see what I'm doing. So 54. We know that there's no perfect cube that's 54. 5 times 5 times 5 is 125, 4 times 4 times 4 is 64, and 3 times 3 times 3 is 27. So we know there's no perfect cube, so can we find an answer to this that is not a decimal approximation? Can I find an actual answer? And I would say yes, we can. And we're going to go back to that factoring. So I'll switch back into my green color. And we've got the number 54. And I chose this specifically for a reason. It's 2 times 27. And we've already done the factorization of 27, but I'm going to go ahead and continue it just for the visual. We know it's 3 times 9, and then this is 3 times 3. And if I go back now and circle my prime factors again, I've got these set of prime factors. So the question again arises is, do I have at least 3 factors inside of 24? Or excuse me, inside of 54. And again, I do. I have these 3, so I could cross them out. Again, move them to the outside. But this time, I still have to account for this 2. So to do that, since I don't have 3 2's, I only have 1 2, I have to write cube root of what remains, cube root 2. And what we find is that the answer for cube root of 54 is 3 times the cube root of 2. So let's go ahead and I can show this on a calculator what this might look like. For the class, I recommend using this web2.0calc.com. It's a really nice calculator. It's got all the functions you should ever need. And we just hit cube root 54, and let's see what it gives us for an answer. It tells us it's roughly 3.7797. Right, and all of these different numbers. Again, this is an approximation, it's not an exact answer, and Math Excel actually wouldn't accept this unless it was asking for a decimal approximation, usually rounded to 4 decimals. So we'd do something like 3.7798, because it's 6 would tell us to round up. So it'd be something like 3.7798. Okay, well, let's go ahead and test the answer that I put in, which is 3 times the cube root of 2. Voila, we got the same answer, 3.779, again rounding to 0.8. So jumping back to here, we found that the cube root of 27 is 3, the cube root of 54 is 3 times the cube root of 2, and that again is because when we did this prime factor tree, we were left with this 2 behind. So we can't just forget about it, we just leave it in this radicand sign. And what you'll see is if we get bigger and bigger numbers, it's possible that we could have multiple things that we would cross out. We might have a couple of sets of 3s. We might have a couple of sets of 2s, and we just move those out front of the radical, and we multiply them. And so if we get any more complicated ones, like maybe 500 or 600 big numbers that are going to have lots of prime factors, just break it down into its smaller parts, go back to what you know, and we should be okay. Hopefully that helped. If you guys have any additional questions, please feel free to give me a call, send me an email, or post something in the forum. Alright, thanks guys.